Assalamualaikum warahmatullahi wabarakatuh. Masih bersama saya, Jarod B. Darmadi. Kita akan membicarakan belt dan bule sampai seri yang ketiga ya sekarang. Ada beberapa video, yaitu 6 seri video dari Profesor Michael Van Biesen dari Loyola Marymount University, LMU, Los Angeles, California, Amerika Serikat. Nih, salah satu favorit saya ini, Profesor Michael Van Biesen ya. Anda bisa mengikuti 6 serinya di alamat link yang tertulis ya di slide. Ya, ada 6 seri. Ini akan membicarakan teori tentang belt, terutama perbandingan T1 dan T2 ya, yang sama dengan sudah kita jelaskan, sama dengan E pangkat mu kali theta ya. Ya, nanti akan dibahas secara mendetail di video itu, disertai contoh-contoh soal yang bagus. Pada video kali ini ya, kita akan mengikuti kuliah oleh Profesor Michael Van Biesen ya, tentang perbandingan ya, tarikan pada sisi kencang dan sisi kendor ya, yaitu T2 dibanding T1 sama dengan E pangkat mu S kalikan beta. Tentu beta adalah sudut sentuh dari belt ya. Baiklah, kita ikuti saja kuliah oleh Michael Van Biesen tersebut ya.
Welcome to our lecture online. Our next topic in friction is called the belt. We're going to talk about belt friction and in particular a flat belt. We're going to derive the equation that determines the difference in the tension on the two ends of the belt when it's situated over a circular drum or peg or some round object here or post around which the belt is wrapped. Notice here that the angle between this line and this line, which delineates the portion of the belt that's touching the drum here, is called beta. We take a small segment of that and call that small little angle d theta, and we're going to take a look at it in a little bit more detail over there. Now notice that the tension T2 here will be greater than the tension T1 if the belt is moving in this direction. There is going to be friction between the belt and the drum or the peg. We'll call that mu sub s. That's going to be the friction between the belt and the drum or the belt and the peg. Now over here we take a look at this small section. We take a small angle delta theta, and we're going to figure out the difference in the tension on the right side and the left side because of this small amount of the belt that's touching the drum here. Also notice that if this angle here is delta theta, then there's delta theta divided by 2 and delta theta divided by 2 relative to the horizontal. The friction force between the belt on that small section and the drum is caused by the normal force times the coefficient of static friction. Now the normal force will be a very small portion of the total normal force found on the entire belt here. So we're going to call that a delta M. Now how do we find the difference in the tension between the right and the left side of a belt going over a drum like that or over a peg like that? Well, the way we can do that is to sum up all the force in the x direction, sum up all the force in the y direction, and solve that simultaneously. So let's try to do that. We're going to sum up all the force in the x direction. And of course, that's going to be equal to 0. Now, what are those? Well, we have the t plus delta t times the cosine of that angle. So we have t plus delta t, that's the force to the right, times the cosine of the angle delta theta divided by 2. Now we have minus this force right here, so minus t times the cosine of delta theta divided by 2. And we have the friction force. That would be minus the friction force, which is delta n times mu sub s. And of course, all that adds up to 0. Now right away you can see that if you have a t times a cosine of delta theta over 2 and a minus t times a cosine of delta theta over 2, that this will cancel out with this one right there. Now we're going to add up all the forces in the y direction. The sum of all the forces in the y direction add up to 0. And now we have the force upward, which is a delta n, so this is equal to a plus delta n, minus the two components of the tensions downward. So on the left side, we have minus tension times the sine of delta theta over 2, and minus tension plus delta tension times the sine of delta theta over 2. Unfortunately here, the t sine delta 2 over 2 doesn't cancel out with that one because they're both negative, and that all adds up to 0. What we're going to do now, though, is we're going to solve the second equation for delta n and substitute that in here because we don't know what delta n is, and so that will help us. That will at least get rid of the one unknown in here. So when we solve for delta n, we take those two, plug and put them on the other side. So basically what we can say is the second equation then becomes the following. 0 is equal to delta t times the cosine of delta theta over 2, and then this is gone, and the t is gone, and then we have the minus. Instead of delta n, we're going to plug in the positive of this, so minus, that gives us t sine of delta theta over 2, and here that would be minus the quantity t plus delta t times the sine of delta theta over 2, and the whole thing multiplied by mu sub s. All right, still quite a mess, but I think we can somehow simplify that. Well,
saya rasa ini kesalahan sedikit ya, ini mestinya plus ya. Biasa ya, plus minus itu ya sering kita lalai dalam hal ini. Ini mestinya plus ini yang ini. Saya rasa.
Well, first of all, we have a minus t sine delta theta over 2, and we have it here again. So we can combine those, makes it a little simpler, and we can factor out a sine theta delta theta over 2. So that gives us the following. 0 is equal to delta t times the cosine of delta theta over 2, and then minus the quantity. So we have 2t, and we have a plus delta theta. Plus delta t, I should say, the whole thing multiplied times the sine of delta theta over 2 times mu sub s. I think that simplifies it a little bit more. What we're going to do next is really a mathematical trick with a little bit of foresight. Essentially, what we want to do is we want to find a relationship between the difference in the tension as a function of the size of the angle. So, that means if I take the delta t here and divided by delta theta, I now have a differential, a form of differential between the change in the tension and the change in the angle, a relationship between the two. And so I think that's how we're going to approach it. Also, we're going to take the limit of all this as delta theta and delta t goes to 0, and so we realize that the sine of, let's say, a sine of x divided by x goes to 1 when you reach the limit. We can simplify this whole equation when we have a little bit of foresight. So this is what we're going to do. We're going to first divide both sides of the equation by a delta theta. So we're going to divide the left side by delta theta, which is still 0, and the right side, on this term, we get delta theta, and here we have, divide this here by a delta theta. Now, here we'd like to have a delta theta divided by 2. For that exact reason, when we take the limit, this will then go to 1. I have a 2 here, so I can take that 2 and put it down here, but then of course I have to worry about that one right there. So I'll put a plus here. I'm going to take this 2, I'm going to factor out a 2, which means I'm going to need a 1/2. Factor out the 2 over here, so that's what I did. I factor out the 2, but of course I multiplied this in, I should get the same thing again, 2t plus delta t. And then I'm bringing this 2 down here. So I'm going to get rid of this 2 and bring it down here. So it's a mathematical trick. Next, what we're going to do is we're going to take the limit. We're going to allow delta t and delta theta go to 0. So we end up with differentials. So that's what we're doing here. So we make the angle smaller and smaller and smaller. So we get an exact relationship between the change in the tension and the amount of angle over which the belt rests on the drum or the peg. So let's do that. So we're taking the limit as delta t goes to 0 and delta theta goes to 0. And when I do that, I get the following thing. So we have 0 is equal to, this becomes dt d theta. That's what we're looking for. Times the cosine of delta theta divided by 2 as delta theta goes to 0. So that means in the limit we get the cosine of 0, which is equal to 1. Minus, here we have t plus a half delta t. Now delta t also goes to 0, so this goes to 0. So we end up with simply a t there, times the sine of delta theta divided by 2 divided by delta theta divided by 2. And again, in the limit, if we have the sine of x divided by x and x goes to 0, that ratio goes to 1. So this becomes 1 as well. And then we have mu sub s. And the equation simplifies tremendously. If we then write it with this on one side and then on the other side, let me go over here. We can now say that the relationship dt d theta is equal to t times mu sub s. So now we need to solve that equation. It's a simple differential equation. We can solve that by separating the variables. So we end up with dt over t is equal to mu sub s times d theta. So this becomes the natural log of t evaluated from t1 to t2, because that's what we want to do. We want to go between the two right there, is equal to mu sub s times the integral of that, and that would be theta evaluated from 0 to beta. Beta, of course, would be the total angle subtended by those two lines that indicate where the belt touches the drum. So what we did really was we integrated both sides. When we do that, we get the following. So on the left side, we end up with the natural log of t2 minus the natural log of t1 is equal to mu sub s times beta, because when you plug in the lower limit, you get 0, the upper limit, you get beta. And then this can be written as a fraction, so we can say the natural log of t2 over t1 is equal to mu sub s times beta. Now that's a good equation. This tells us the relationship between the difference in the tension between T2 and T1 and the static coefficient of friction and the angle that subtends. But it's better if you take both sides of the equation and make it the exponent of E. When you do that, when you take the analog, in other words, you get T2 divided by T1 is equal to E to the mu sub s times beta, like that. And that's a better way to write the equation. Which means, if you know the coefficient of static friction between the belt and the drum, and you know the angle over which the belt subtends, how much of the belt touches the drum, then you can figure out the difference in the tension, or the ratio in tension 2 divided by tension 1. If you know one of them, you can calculate the other one. And we'll show you some examples of how to do that. This is, by the way, a very handy equation to use in many examples, in many situations.
Saya rasa jelas ya yang penjelasannya. Mungkin perlu dijelaskan ini. Yang sin X dibagi X itu sama dengan 1 ya. Untuk X mendekati 0. Ya, bisa dibuktikan ya, tapi X dalam radian ya. Itu. Kemudian akhirnya kita sampai kepada persamaan yang sederhana di sini. Tentang T2 dibanding T1 yang sangat aplikatif ya, ini persamaannya mudah.
Where you're trying to figure out the difference in the tension of a belt that goes around the post or goes around the peg, and you're applying pressure or tension on both sides on that belt. So this is how you get the equation. Now we're going to show you some examples of how to apply the equation.
Oke, begitulah sudah selesai bagaimana menurunkan rumusnya. Mungkin berikutnya akan diberikan contoh soal. Pada video ini ya, akan diaplikasikan rumus sebelumnya, yaitu T2 bagi T1 sama dengan E pangkat mu S beta ya, pada tali yang dililitkan pada tonggak atau apapun ya. Akan kita hitung berapa gaya yang diperlukan untuk menahan agar tali tidak slip.
Welcome to our lecture line. Here's our first example of how to work with that equation that deals with belt friction. What we have here is we have a rope that's wrapped around the post. It's wrapped around twice. The rope begins to make contact right here with the post, goes all the way around once, goes all around again the second time, and then of course after this it no longer makes contact with the post. So it's exactly twice around the post. And there's a force of 1,000 newtons pulling on this side of the rope. The question is, how much force is required over here to hold the rope from slipping so that the rope is stationary? We're going to calculate it 3 times with 3 different coefficients of static frictions, 0.2, 0.4, and 0.8. Notice that each time we double the coefficient of friction from before to see what effect it will have on the amount of tension required or force required to keep the rope from slipping. So what we can say here is that the equation we found on the previous video, T2 divided by T1 is equal to E raised to the coefficient of static friction times the angle of contact. So in this case, the angle of contact would be 2 complete rotations. That would be twice 2 pi, or a total angle of 4 pi radians of contact. Now we're looking for T1, so this equation can now be solved for T1. Say that T1 is equal to T2 divided by E to the mu sub s times beta. And we're going to calculate that for 3 of these coefficient of frictions. So we're going to use the first one where mu sub s is equal to 0.2. That means that T1 will be equal to 1,000 newtons divided by E to the 0.2 times 4 pi. 2 complete revolutions is 2 pi radians, and yes, we do have to use radians for the angle, and then with the calculator we get the following: 0.2 times 4 times pi, raise that to as an exponent, and times 1,000 equals, and that gives us exactly 81 newtons. So it requires T1 equals 81 newtons, the force required to keep this rope from slipping, which is kind of nice. You see here that when you apply a force of 1,000 newton here, you only need 81 newtons to keep that rope from slipping. And that is if the coefficient of friction is 0.2. What happens if the coefficient of friction is 0.4? How does that change things? And initially you might think, well, if it's double the coefficient of friction, you expect maybe half the tension, but that's not the case. This is kind of a unique situation. It's not a linear function, and so let's see what that happens. We get mu sub s now equal to 0.4, so we get T1 is equal to 1,000 newtons divided by E to the 0.4 times 4 pi. And let's see what happens now. So we have 0.4 times 4 times pi e to the x inverse times 1,000 equals, so it's only 6.56 newtons. T1 is equal to 6.56 newtons. Notice by doubling the coefficient of friction, we now require less than 1/10 the tension to keep the rope from slipping. Now let's go one more. Let's say the coefficient of friction is 0.8. That's not a usual case, but just to see how this works. Let's try mu sub s equals 0.8. That gives us T1 is equal to 1,000 newtons divided by E to the 0.8 times 4 pi. And let's see what that now becomes. So we get 0.8 times 4 times pi as an exponent. Take the inverse of that, times 1,000. And now we take just a small fraction of a newton, 0.043 newtons. That's almost hard to believe. And that's indeed the case. It turns out that when you wrap strings or ropes or cables or anything around the post a number of times, the amount of tension you need on the other side to keep the rope from slipping is actually quite small and becomes very small as the coefficient of static friction increases. So now in the next example, we're going to do something similar, but now we're going to change the number of times we wrap the rope around the post to see how that affects how much tension you need to keep the rope from slipping. That's how it's done.
Saya rasa cukup jelas ya soalnya ya, dengan mendobelkan ya koefisien gesekan, maka daya yang diperlukan untuk menahan semakin kecil, bahkan tidak hanya separuhnya ya, tapi jauh lebih kecil, hampir 1/10-nya tadi. Oke. Pada video ini ya, yang ketiga ya, jumlah lilitannya ini yang dinaikkan ya, dari 2, 1 ya, 2, terus kemudian menjadi 4 lilitan ya. Bukan koefisien geseknya. Koefisien geseknya dianggap tetap 0,4. Mari kita ikuti kuliah selanjutnya dari Profesor Michael Van Biezen ya.
Welcome to our lecture line. In this example, we're going to wrap the rope around the post once, twice, and 4 times. So in essence, each time doubling the number of turns or number of loops around the post. We're going to keep the coefficient of static friction the same, and what we want to do is calculate what the tension will be over here in order to keep the rope from slipping if we apply a force of 1,000 newtons on the other side. So again, we use the same equation as before. We solved it for T1, and now we can calculate it for each of these 3 cases. T1 is going to be equal to 1,000 newtons applied on one side, divided by E to the coefficient of static friction, 0.4, times only 1 turn, which is 2 pi radians. And now we can see what that is equal to. Take the inverse and times 1,000. Equals, and it gives us 81 newtons. So T1 is equal to 81 newtons. Okay, what we're going to do now is we're going to do it again, but now we take 2 turns around the post and see what happens. All right, so that gives us T1 is equal to 1,000 newtons, 0.4 times 4 pi. Again, we take 0.4 times 4 times 1,000 equals, and it gives us 6.56 newtons. So what's interesting here is even though we simply doubled the number of turns from 1 to 2, the amount of tension required to keep the rope from slipping dropped dramatically from 81 newtons down to less than 10% of the original amount. So now let's do it 4 turns and see what happens. Now we get T1 is equal to 1,000 newtons, that's the coefficient of static friction, by times 8 pi, which is 4 times around. See what we get? 0.4 times 8,000 equals, and now T1 is just a very tiny 0.043 newtons. Notice that if you compare this to the previous example, that doubling and quadrupling the coefficient of static friction had the same effect as doubling and quadrupling the number of turns around the post, because both of them are part of the exponent of the number E, and because of that, the tension dramatically, or the tension required to keep the rope from slipping, dramatically decreases. And that's how you can see the relationship between the tension, the coefficient of friction, and the number of turns in the rope. And that's how it's done.
Oke. Saya rasa sudah jelas ya, jelas sekali. Ya, kesimpulannya dengan mendobelkan, mendua kalikan koefisien gesek, ya hasilnya sama saja dengan melilitkan rope atau talinya 2 kali pada tonggak itu ya. Begitulah ya tentang beda tarikan ya, sisi kencang dan sisi kendor. Mudah-mudahan dengan 3 gambaran soal tadi ya, memudahkan kita untuk mengerti tarikan sisi kendor dan sisi kencang pada sabuk ya, yang tentunya tidak sampai 1 atau 2 lilitan ya sudutnya ya, terutama yang bule kecil sudutnya pasti di bawah 180 derajat atau pi ya, di bawah pi. Dan untuk sudut yang kecil maka itulah yang rentan untuk mentransmisikan daya, ya kan? Karena dibatasi oleh nilai beta ya, sudutnya yang kecil ya, dibanding jika untuk pule besar sudut betanya di sini ya lebih besar dibanding pule yang kecil. Pada contoh soal berikutnya ya ingin dihitung maksimum momen yang bisa ditransmisikan ke pule A ya. Tentu ini enggak jelas putarnya, umpama putarnya ke sana ya mestinya searah jarum jam misalnya, maka sini sisi kencang, sini sisi kendor yang bisa dihitung dengan rumus sebelumnya ya. Jika diketahui koefisien geseknya sekian ya. Tentu perbedaan momen adalah sisi kencang dikalikan jari-jari yang arahnya searah jarum jam, sedangkan sisi kendornya arahnya berlawanan jarum jam dikalikan jari-jari. Prinsipnya itu saja ya, dan kita menggunakan rumus perbandingan antara tegangan yang kendor dan tegangan kencang sebelumnya. Baiklah, kita ikuti saja kuliah oleh Profesor Michael Van Biesen berikut ini.
Welcome to our lecture online. Our next example deals with a belt drive. We have two pulleys, pulley A and pulley B, and pulley B is driving pulley A by causing a tension to exist on this drive belt right here. That tension, of course, is created by pulley B turning, and so what we can say is that the tension here, let's call that T2, and T2 is going to be at maximum 800 newtons. There's a limit as to how much force we can apply and how much tension we can put on this belt, so we don't want that belt to break. What we're trying to calculate is the maximum moment we can apply on A using this belt drive system like this. So what that means is we're going to have to find the tension over here and the tension on the other side of the belt, T1. And of course, that will depend upon what happens on pulley B right here. Once we calculate T2 and T1, we can then calculate the moment on pulley A. Alright, let's go ahead and use our equation. We know that T2 divided by T1 is equal to E to the coefficient of static friction times the angle of contact. Now notice if this is a 20-degree angle with the horizontal, we have a similar situation here. This must be a 20-degree angle here and a 20-degree angle there, which means that the angle of contact beta here on pulley B is going to be 180 degrees, which would be half a turn, minus 2 times 20 degrees, which is 140 degrees, which of course we're going to have to convert to radians. We're given the coefficient of static friction and we're trying to find T1. That means that T1 is equal to T2 divided by E to the mu sub s times beta. So in this case, we have a maximum tension of 800 newtons divided by E to the 0.3, and beta will be 140 degrees, but we'll have to convert that to radians, which is pi divided by 180 as the conversion factor. All right, now we're ready to find T1. So we have 0.3 times 140 times pi divided by 180, and that becomes the exponent of e to the x. Take the inverse of that, times 800 equals 384 newtons. So T1 is equal to 384 newtons. Now we're ready to calculate the moment we can apply to A. Notice that the tension here is equal to 800 newtons, and the tension here is equal to, that's newtons, and over here it's 384 newtons. So the moment on A is equal to the net tension on that, which would be 800 minus 384, 800 minus 384 newtons times the moment arm, or in this case, the radius of the pulley, which is 15 centimeters, converted to meters, which is 0.15 meters. And that will be the moment, the maximum moment we can apply to A. And so the maximum moment on A is going to be equal to 800 minus 384 multiplied times 0.15, and that gives us 62.4 Newton meters. Quick check. 800 times minus 5 equals, yes. Oh, yeah, 62.4 Newton meters. So, again, the way we do that is, there's the pulley that's driving the belt. We have an angle of contact, which is 180 minus 40. We have a coefficient of static friction, and then using the equation that we found, we can then calculate the tension on the other side of the belt if this tension here is a maximum of 800 newtons. Notice that this pulley will be turning in a clockwise direction, pulling on this belt, and there'll be less tension on this side because of the difference in tension on both sides of the pulley. That difference in tension then applies to this pulley, and then we can find the moment by taking the difference in the tension times the moment arm. That's how it's done.
Oke, baiklah, saya rasa sudah jelas ya apa yang disampaikan oleh Profesor Van Bisen. Baiklah ya, pada video berikutnya ya kita akan mengikuti kuliah Profesor Van Bisen ya dengan contoh soal yang lain ya, yaitu dua massa digantungkan dan kalungkan pada semacam tonggak gitu ya. Akan dicari berapa M2 maksimum ya sebelum massa M1 bergerak naik atau sebelum ini terjadi bergeser ya, slipping atau bergeser ke arah bawah M2-nya, M1-nya ke arah atas ya. Tentu kita masih menggunakan persamaan sebelumnya, yaitu T2 banding T1 ya, sama dengan E pangkat mu S kalikan beta ya. Baiklah, kita ikuti saja kuliah oleh Profesor Van Bisen berikut.
Welcome to our lecture line. Our next example deals with a rope that's suspended across a peg like this. It has two masses attached to the end of the rope. We have a known mass on one side, 5 kilograms, and an unknown mass, M2, on the other side. Assuming that the coefficient of static friction is 0.4, and of course the wrapping of the rope would be 1/2 the complete circle around the peg here, what would be the maximum mass you can place on this side before they both start slipping, before they start moving? Obviously, once they start moving, the coefficient of kinetic friction is smaller, and of course the thing will begin to accelerate. The whole system, I should say, will begin to accelerate. So what's the maximum M2 we can attach here before everything starts slipping? Well, what we need to do here is again start with the same equation, that T2 over T1 is equal to E oh man. Oh, that was a tickle like crazy. Is equal to E to the coefficient of static friction times the angle of wrapping, of the string wrapping around the peg. Since we're looking for T2, we can say that T2 is equal to T1 times E to the mu sub S times beta. All right, T1 is simply the weight. Oh, I got a cough again like crazy. Oh, there's something in the air up here. You get it too, right? Okay, I think I can try to continue. T1 is going to be equal to the weight of this object, so we can then write that T2 is equal to M1G times e to the coefficient of static friction, 0.4, and the angle would be a half of 2 pi, half a complete circle, which would be pi. That will tell us the tension we can place on, well, the tension that can be on this side before everything starts slipping. So 0.4 times pi, make that the exponent. And so what that tells us is that T2 is equal to 3.514 times M1G times the weight of the other side, like that. So in other words, we could place an object here that has 3.514 times the mass of M1. Therefore, we can say that M2 is equal to 3.514 times M1. So we multiply that times 5, and we get 17.57 kilograms as being the maximum weight, or I should say the maximum mass that we can place on this side before everything starts slipping. And that's how it's done.
Oke, contoh soal yang bagus. Video berikutnya ya, ini hampir sama dengan soal sebelumnya, tetapi dililitkan 2 kali di sini, dan ada mu S sama dengan 0,3 ya. Artinya koefisien gesekan antara tali dengan tonggak ini adalah 0,3. Kemudian ada mu K 0,25. Jadi kalau dia bergerak, maka kita memakai nilai 0,25. Ya, 0,3 ini yang kita pakai untuk soal A ya, ketika akan bergerak M1-nya ya. Terus kemudian jika sudah bergerak kita menggunakan mu K ya, yang harganya lebih kecil. Tentu kalau sudah bergerak gaya yang diperlukan di F ini lebih kecil ya. Kalau beban di sini terlalu kecil, maka akan sebaliknya dia akan bergerak ke arah kanan, atau M1-nya akan turun ya, dan M di sini akan naik. Itu yang menjadi soal yang kedua ya, dan kita ikuti saja penjelasan kuliah dari Profesor Michael van Biezen ya.
Welcome to our lecture online. Our next example deals with a similar situation as before, but here we have the rope wrapped around the peg 1.5 times. We have a mass, let's say, equals to 10 kilograms on this side, and we're going to try to find 3 things. First of all, the force required to start lifting M1. What is the maximum force by which we can pull on this side before M1 begins to move up? Once we overcome the static coefficient of friction, or the static friction, then of course we have kinetic friction. Then what we need to do is find the force required to keep M1 moving up at a constant speed, which is going to be less than the force required to get it moving. And finally, what if we reverse things and we allow M1 to slide down, or at least keep it from sliding down? What's the force required on this side to keep M1 from sliding down? So those are the 3 things we're trying to answer. For all 3, we're going to use the same equation. We started with T2 divided by T1 is equal to e to the mu in the first case. So for part A, we're going to use mu sub s times the angle beta. Since we're looking for T2, we could write that T2 is equal to T1 e to the mu sub s times beta. And so this will be equal to T1 is going to be the weight of M1, would be 10 kilograms times the acceleration due to gravity, 9.8 meters per second squared. And we multiply that times e to the 0.3, because we're going to use coefficient of static friction, times the angle 1.5 times around the peg. That would be 3 pi radians. Okay, let's see what the force is in this case. 0.3 times 3 times pi. Make that the exponent of E times 98, and that will require a force of 1,656 newtons. Notice that's quite a bit of force. With an object that only has a mass of 10 kilograms, it requires quite a bit of force to start moving it up if the rope is wrapped 1.5 times around the peg and the coefficient of static friction is 0.3. You can see the advantages of pulleys, which would eliminate that friction, of course. Now let's see what it would take to keep M1 moving upwards once we've exceeded the force required to overcome the coefficient of static friction. Now you would think that since there's such a small difference between the static coefficient of friction and the kinetic coefficient of friction, that it wouldn't drop by that much. But let's find out. So for part B, we have T2 is equal to T1 times e to the mu sub k. Now we use a coefficient of kinetic friction times beta. So this becomes 10 times 9.8 times e to the 0.25 instead of 0.3 times still 1.5 times wrapped around. So this becomes 0.25 times 3 times pi, use that as exponent, and times 98. And notice at this point it's 1,034 newtons. So quite a drop by changing from static to kinetic coefficient of friction. So you can see that if you have a rope wrapped around a peg, once you get the thing moving, then everything will start moving much more easily with a lot less force required. Now for the third part, we need to figure out what force is required here to keep M1 from going down. All right, so in this case, we're going to have to reverse the order. This now becomes T2, and this now becomes T1. And so for part C, we can now say that since now we're looking for T1, we can say that T1 is equal to T2 divided by e to the mu sub s times beta, the angle that the rope is wrapped around the peg with. So this is equal to T2, that would be, well, in this case, since this is T2, that would be 10 kilograms, the weight of that object times 9.8, and divide that by e to the, again, we go to the static coefficient of friction, 0.3, because nothing is moving yet, and 3 pi for 1.5 turns. So 0.3 times 3 times pi, make that the exponent, bring that to the numerator, and times 98 equals, and it only will require 5.8 newtons. So you can see that since there's so much friction between a rope and a peg like that, we only need a force of 5.8 newtons to keep a 10 kilogram object from sliding down. Since it's not a pulley, there's lots of friction there and not a lot of force required to keep it from sliding. And that's how it's done.
Oke ya, begitu saya rasa sudah jelas sekali ya, kuliah oleh Profesor Van Beysen. Berikut ini juga ada 4 video yang cukup informatif dan baik untuk diketahui. Yang pertama, halamannya seperti itu, membicarakan secara umum tentang flat belt ya khususnya. Terus yang link nomor 2, ini membicarakan bagaimana agar flat belt tetap ada di pule ya. Ternyata bentuknya itu tidak benar-benar flat tetapi cembung ya, sehingga pule cenderung terdorong sehingga sabuk cenderung terdorong ke tengah. Kemudian yang ketiga ini membicarakan secara umum ya tentang belt, khususnya V belt ya. Bagaimana jika harus berpasangan antara pule yang besar dan pule yang sangat kecil ya, atau extra small pule ya. Maka yang pasti sudut sentuhnya atau wrap-nya itu akan kecil, kemudian mudah terjadi slip, dan daya yang ditransmisikan juga terbatas ya. Kemudian juga dibicarakan bagaimana kalau tarikannya terlalu besar ya, maka tentu akan jadi problem ya, terutama di piring kan, atau bantalan dari poros. Kemudian memilih V belt ya harus sesuai groove-nya dengan beltnya yang ketiga. Kemudian jarak antar sabuk ya perlu didiskusikan, yaitu antara 2 kali diameter yang besar jarak antar porosnya sampai 3 kalikan diameter yang besar ditambah diameter yang kecil ya. Kalau terlalu jauh jaraknya ya, artinya untuk belt tertentu akan sangat kencang ya, justru menimbulkan vibration ya atau getaran ya, itu dihindari. Kemudian juga dibicarakan kalau terpaksa dipakai bule yang kecil ya digunakan idler bule ya. Tetapi dengan idler bule ya akan ada masalah baru lagi, yaitu fatigue bending. Karena bule harus berbelok-belok begitu sabuknya dan akan mengalami tarik tekan, maka akan terjadi fatigue bending ya, umurnya berkurang. Yang ketiga ya power rating ya untuk belt-belt tertentu ada power rating yang bisa ditransmisikan ya. Jika tidak mencukupi ya digunakan 2, 3, 4 bahkan bisa 12 sabuk secara bersama-sama dalam satu bule dengan multi groove. Daya juga ada ya batasannya untuk bule dengan diameter tertentu, karena tentu lengan gaya atau lengan kuasanya berbeda untuk bule yang besar maupun yang kecil. Begitu yang ketiga ini cukup banyak yang disampaikan. Ya. Kemudian yang terakhir ya, ada beberapa informasi yang menarik juga, yaitu secara umum V belt kelebihannya apa, jenis-jenis V belt apa ya, juga didiskusikan tentang coding ya, pengkodean jenis V beltnya. Itu seri 4 video berikutnya setelah 6 video sebelumnya dari Profesor idola saya. Baiklah, kita akan melihat ya overview tentang penggunaan V belt yang masif ya, dan ada contohnya di situ ya, ditunjukkan pada video berikut ini.
The driving force behind heavy industry is the practical transmission of motive power. Prior to the development of compact electric motors, the belt and line shaft system was used to distribute power from source to machinery in most industrial workshops and factories. The system is comprised of 3 basic elements: shafts, pulleys, and belts. Central power would be derived from a machine generating rotary motion such as a steam engine, a turbine, or a water wheel. In the case of our machine shop, power is supplied via an electric motor. A belt is looped at one end around a pulley driven by the motor, and at the other end around a pulley fastened to a shaft, causing the shaft to rotate. Belts looped around other pulleys fastened to the shaft then transfer that rotation to other shafts or directly to machines. An open belt connecting 2 pulleys causes the pulleys to rotate in the same direction, but a belt can also be made to form a crossed loop to turn the pulleys in opposite directions. Power from the line shafts can be engaged to the machines by shifting the belt from a loose pulley or idler turning freely on the shaft to the drive pulley fastened tightly and rotating with the shaft. The line shaft system in our shop drives a collection of machinery, some of which was once used by the Waltham Bag and Paper Company, and others gifted to us by various individual donors.
Ya, begitulah contoh ya, meskipun cuma di museum ya, sekarang tidak begitu ekstensif lagi mungkin digunakan belt seperti saat zaman dulu ya, masih awal-awal di era dunia revolusi industri. Pada video berikutnya ini ditunjukkan bahwa bentuk dari bule itu untuk flatbed tidak rata seperti itu ya. Untuk menjaga beltnya tetap ada di tengah, itu bentuknya agak cembung gitu ya. Ya, ini lebih dievaluasi dengan lebih detail tentang bulenya. Oke, silahkan diikuti videonya.
Okay, well, just a really short one here for you. I've seen on a lot of YouTube videos and comments, people are saying, how does a flat belt stay on the pulley? And I thought, well, I'll show you. So this is a pulley, a flat pulley, off of a mill or a thrasher box or something. I don't really know what it's off. And it looks fairly flat, doesn't it? So obviously the belt would run on there and off to the machine. But if we put the ruler on, okay, you can see that there is a slight gap. So what's happening is the belt actually moves up. So the top is higher than both ends. And what that means is, when the belt is put on, the belt will always want to run to centre. That's why sometimes you see the belt sort of rocking backwards and forwards. What it is, it's because it's curved going up. That keeps the belt in the centre. So next time you go to a rally and somebody says, how does that belt stay on? Either direct them to this video or you can feel really smug.
Oke, begitulah yang menyebabkan belt tetap terjaga di tengah untuk bule flat belt. Pada video berikut ya akan ditunjukkan bagaimana semacam tip and trick ya memilih V belt ya, dan ditunjukkan bagaimana ya menghitung secara cepat tentang V belt ini. Silahkan disaksikan videonya dan bisa diikuti di link aslinya yang diberikan sebelumnya tadi ya.
So let me give you a couple quick tips about designing with V-belts. Here I have a relatively stiff V-belt. I want to use this to illustrate problem number 1 with using a very small pulley. And that's a concept called wrap. As you can see, when I pull this V-belt tight, you can look at the pulley and see that I don't have a whole lot of engagement on the actual pulley itself. The angle of contact that I have between here and here on this pulley is called wrap. The greater your wrap, the more power you're going to be able to transmit with your pulley. And that's the issue with using very small pulleys. They just don't allow for very much wrap. Designing a machine with a very small pulley like this means that this pulley is going to slip. When it slips, your first temptation is to say, my belt is not tight enough. But making the belt tighter leads to a different problem. You don't actually want your belt to be that tight. The best way to do it is you want it to be snug and then have just a little bit of slack. You should be able to flex your belt just a little bit. So we select a larger pulley. We try not to make it too tight, and this will allow us to get much more wrap. We can transmit more power and have less vibration. There's another factor you want to consider, and that is actually the groove in your pulley. You want to be sure that if you have an A-style groove in your pulley, that your belt is also A-style. And this is easy to check. You just need to look at the value when you purchase your pulley and then buy a belt that matches that. Looking here at my Shigley's Mechanical Engineering Design book, there's a section here on the belt section, and this just describes the geometry of the belt. But you'll notice way over here it talks about the motor's power range, and then there's a minimum sheath. So 75 millimeters is almost 3 inches in diameter. Your pulleys really shouldn't be much smaller than this guy. That's 3.5. One more factor you want to consider is the distance between your pulleys. And we're referring to the center to center distance. This guy is your driver, which would be the case for me. and the motor is pulling like this, I want you to notice that this side tightened up and this side went slack. So this is considered the slack side, and as you increase the center to center distance, you're going to get more and more slack, more and more vibration here, and that's going to reduce the life of your belt. According to my Shigley's book, you don't want to go more than 3 times the sum of the 2 diameters. So you would add the 2 diameters together. This one's about 5 inches, and we'll say this is 3. So that's 8 inches times 3 would be 24 inches, would be the maximum distance you'd want to have between these 2 pulleys. The minimum distance would be the diameter of one sheave. Notice that here you've got just the radius, and so you don't want to go less than the diameter of the larger sheave. One more option to consider when you really want to use a very small pulley would be to use an idler. An idler pulley would just be another pulley placed on the outside, which would push in. It would increase your wrap and give you more traction throughout your system. The only problem that I have with this personally is that you are increasing the number of bends in the belt, which will decrease the life of the belt because it's constantly changing shape every time it goes around the pulley. But it depends upon the rating of the belt and the horsepower being delivered. If you have a belt that's rated for, say, 1 horsepower and you're only transmitting 1/3 horsepower, it's probably not even worth worrying about. Another thing to keep in mind is the amount of horsepower one belt can deliver. And that's why I've got 2 V belts here. This 4 horsepower motor was a little bit too much for one belt, but 2 belts can handle it just fine. And there are calculations for these kinds of things. You just need to see what your belt is rated for, and then you can decide how many belts you need. Now, when you start thinking about industrial applications, you can buy sheaves that have 10 or 12 grooves, and they'll go as big as you need for your V-belt application. But in the home shop, this is probably the most you would ever need with a 4 or 5 horsepower motor. Alright guys, I've got one more tip for you, and that relates again to the size of your pulley. You can look at my setup here and you say, well, Jeremy, you've got almost a 7-inch diameter pulley here, 6 3/4 actually, and then the 2 pulleys you made over here are 14.5. Why not use a small guy like this, maybe a double groove pulley, but a much smaller OD? Then you could save a lot of work, make that guy a lot smaller. But there's a hidden penalty for using this small guy here, and it's not about the angle of wrap that I showed you earlier. Before I tell you the problem, I want to show you a chart from a website that I pulled up earlier who sells V-belts. If you look at this first line going from left to right, it shows at a fixed RPM, as the diameter of the sheave gets larger, the horsepower rating goes up. And that might seem counterintuitive, but there's a very good reason for that. Your pulley is a lever. Consider for a moment, this is your axis of rotation, and this is where the force is being applied in order to give you different amounts of speed and torque. For the same horsepower rating, if I use a smaller pulley, I have to apply more force because my lever is shorter. If you think about wrenches, and you have a wrench like this and a wrench like this, if I want to apply the same amount of torque on this shaft, I'm going to be doing less work with this guy than I would with this guy. And it's the same thing for your V-belt. As the pulley gets smaller, it has to work harder to deliver the same horsepower. Alright, here comes my favorite part about posting videos, and that is reading the comments when the video goes live. Let me tell you, I've got this amazing group of tinkerers, mechanics, engineers, all these people who give me great feedback after every video. I will take some of my favorite suggestions that come in, because I'm sure some will, and I will add those to the video description, so be sure to check out the description. And I'll also add any technical corrections if I made any mistakes in the video. Well, I sure hope you found that helpful. Thanks for watching.
Demikianlah ya presentasi yang menarik dan 7 tip and trick cara memilih V-belt. Pada video berikut ini ya akan dijelaskan lebih detail ya tentang V-belt ya, bagaimana dia secara efektif ya bisa memindahkan daya dari satu poros ke poros yang lain. Kemudian detail keuntungan dari V-belt juga disampaikan ya secara singkat dan komprehensif, juga bagaimana memilih V-belt ya yang mulai menggantikan tali atau rope itu di awal tahun 1900 ya, dan terbukti V belt memang lebih efektif dibandingkan rope atau tali. Baiklah, kita ikuti saja videonya.
This program will focus on a small but crucial component of the power transmission process, the V belt. The program will explain why V belts are so effective, detail their advantages, and show how to identify and select the correct style of belt. V belts are simply transmitters that effectively link a power drive to a needed function. The belts are easy to select, simple to install, and offer years of reliable performance. The first V belts appeared in the early 1900s. They were cut from leather and fabric, and they replaced existing drives which used rope running in V grooves. Modern V belts are constructed differently. They are made of natural and synthetic fibers and rubber, but they still utilize the original wedge concept to harness power. The wedge-shaped belt fits into the wedged groove of the sheave to create a matched fit. When the drive is activated, the pulling power comes from the action of applied tension, which forces the belt to wedge tightly into the sheave groove. By using the wedge principle, the V-belt gains the advantage of tremendous gripping power. Besides this power advantage, the V-belt offers many other advantages for industry in its efforts to reduce equipment repairs and minimize downtime. When an operation demands efficiency and minimal maintenance, the V-belt drive is the logical choice. Unlike roller chain, V-belts require no lubrication. They offer smooth starting and running. They cover wide horsepower ranges. They permit a wide range of driven speeds. They are quiet and efficient. They dampen vibration between driving and driven machines. And they act as a protective device because they refuse to transmit a severe overload of power, which could damage equipment. Finally, V-belts wear gradually, making corrective maintenance simple and easy. V-belts are so effective that even when proper installation and maintenance procedures are neglected, the belts will operate with some degree of success. A V-belt is designed around two concepts, strength and flexibility. The strength is provided by a row of tensile cords. The cords serve as the load-carrying component and are made of twisted synthetic fiber. The compression section is made of synthetic rubber. It supports the tensile cords evenly and compresses while bending around the sheaves. Conversely, the tension section, located above the cords, is designed to stretch as the belt bends around the sheaves. The cover or top fabric is made of a rubberized fabric designed to provide wear resistance and increase belt flexibility. In more recent years, belts with a cog construction have become popular for specific applications. The cogs offer greater flexibility, and with proper usage, it is possible to get up to 25 to 50% more belt life than a standard V-belt. The cogs make it possible to use smaller diameter pulleys, resulting in more compact drives. Additionally, standard V-belts generally have an ambient temperature limit of 140 degrees Fahrenheit. A cog belt can operate slightly above this limit because of its ability to minimize heat buildup. While the V-belt's basic design may be simple, the applications demanding its services are complex. That's why the standard V-belt has evolved and expanded to fit the needs of industry. The increasing demand for higher productivity has resulted in a wide variety of V-belt designs capable of handling specific applications. Each V-belt type has a specific design for a specific function, and the identification nomenclature is different for each belt. The differing ID numbers make identification and selection simple. This allows for quick replacement and minimal downtime. If the ID numbers have been worn away, the belt size can be checked by using a V-template gauge. The most common belt type is the classical or conventional V-belt. The classical is also known as a multiple belt because one or more belts of the same cross-section can be used on one multiple drive. Typical applications for the classical V-belt include industrial fans, blowers, conveyor drives, oil field equipment, and agricultural equipment. Classical belts are also available in the cog construction. The dimensions of the classical belt are identified by the prefixes A, B, C, D, and E. Each prefix indicates a standard top width of the belt in inches. For example, A indicates 1/2 inch top width, and B indicates 5/8 inch top width. The classical belt is also available as a cog belt, offering a higher capacity. The cog belt prefixes are AX, BX, and CX. The second size dimension is length. The true length of a classical belt is defined by a datum length. The digits indicating the nominal size represent an approximate inside length. For example, an A42 belt indicates a top width of 1/2 inch and datum length of 43.3 inches. The approximate inside length is 42 inches. Another common belt type is the fractional horsepower or single V belt. FHP belts are light-duty belts used when the prime mover is a fractional horsepower motor or small engine. Typical applications include appliances and many small machines in industry and around the home. The top width dimensions of the FHP belt are identified by the prefixes 2L, 3L, 4L, and 5L. But while the digits in the classical designation indicate inside length, the digits in the FHP belt indicate approximate outside length. For example, a 3L 380 belt means a 3/8 inch top width, the L indicates light duty, and 380 means 38 inches outside length. Another popular belt type is the narrow or V series belt. Although narrower, their tensile and load-carrying sections are as strong as those in the classical belt. The narrow belt is designed this way to allow for more work in less space. The applications are the same as classical belt applications, and the belts are used with multiple drives also. The narrow belt works best with compact drives, drives of lesser weight, and drives needing greater horsepower capacity. Cog construction is very popular for narrow belt applications, and narrow belts also use the X to denote cog construction. Top width designations for narrow belts are 3V, 5V, 8V, 3VX, and 5VX. Narrow belts are measured by effective length in a standard measure pulley, or the approximate outside length of the belt. Therefore, a 3VX 450 belt would indicate 3/8 inch top width and 45 inches approximate outside length. The X indicates a cog belt. The need to resist drive instabilities brought about the joined belt. Joined or banded belts consist of 2 or more belts whose top fabric is joined to create one unit. This design is effective for pulsating drives that would cause single belts to turn over in the pulleys. Joined belt ID numbers use the same top width designations as the classical and narrow belts. To get the part number, simply add the number of belts as a prefix to the standard belt number. For example, a 3-belt wide BX75 belt would be labeled a 3BX75, the 3 designating 3 belts, and BX75 for the belt size. The great variety of drives and innovative machines has brought about the need for a number of belts for special applications. A good example of a specialty belt is the double V or Hexagonal V Belt. While the driven shafts on most machines rotate in the same direction, some applications call for the shaft to rotate in a direction opposite to that of the driving shaft. The double V belt was designed for these drives because the belt will drive from either its top half or its bottom half. The construction of a double V belt is similar to the classical design. Therefore, the ID numbers are easily identified as AA, BB, and CC. An AA42, for example, is the same as the A42 or AX42 on a standard measure pulley. Other specialty belts have appeared in recent years, and with the advent of different drives, these belts are in great demand. One specialty belt with a very specific function is the variable speed belt. Variable speed belts are designed to provide speed variation in a drive by working with adjustable shifts. Other specialty belts include open-end V belts, V-ribbed belts, and dry can belts.
Oke ya, begitulah video yang cukup panjang presentasi tentang V Belt ya. Cara pemilihannya dan jenis-jenisnya itu diwakili oleh standar code ya, code tertentu untuk V Belt-nya. Tentu kita tidak perlu menghafalkan ya standar code-nya ya, perlu ditelaah tapi ya, dan silakan membuka tabel dan buku-buku bagaimana code itu memiliki arti dari sebuah V Belt. Demikianlah ya, banyak informasi ya, yang bisa kita akses secara online ya, di YouTube maupun di media yang lain ya. Zaman sekarang informasi semudah Anda menekan tombol di keyboard di laptop Anda ya, atau touchscreen di handphone Anda ya. Dunia benar-benar terhubung, informasi beredar bebas ya. Tinggal kita ingin mendapatkan informasi tentang apa ya. Seperti saya sajikan ya, tadi kita seperti kuliah di Los Angeles bahkan, dan kita dapat informasi dari praktisi ya, yang menggunakan belt maupun bule ya. Zaman sekarang luar biasa, waktu saya kuliah dahulu kok mencari informasi berupa film, mendapatkan buku dosennya apa itu aja susah banget ya. Ketemu dengan dosennya satu semester empat kali dan informasinya tidak begitu jelas. Zaman sekarang Anda bisa mengikuti dosen dengan jelas, kemudian Anda bisa memperkaya di media online yang tersedia dan hampir tidak ada batasnya. Dunia informasi memang berkembang sangat pesat ya. Oke. Untuk itu saya ingin memberikan mahasiswa PR ya. PR-nya yaitu carilah video di YouTube tentang belt dan bule ya. Tentu selain yang telah saya berikan ya. Kemudian setelah Anda mencari, ya mungkin di-download dulu, kemudian buat review dari video tersebut ya. Reviewnya paling tidak lebih boleh, tetapi paling tidak informasi baru apa yang Anda peroleh dari video tersebut ya. Terus kemudian dari video itu kontribusi apa yang bisa ditambahkan untuk memperkaya pelajaran elemen mesin khususnya sabuk dan bule yang telah diberikan ya. Oke, itu paling tidak ya. Yang memberikan teori dasar lebih saya sukai dibanding sekedar informasi biasa ya, yang seperti videonya tentang yang diberikan profesor dari Los Angeles tadi kan YMU ya, kan menarik ya, memberikan teori dasar yang seperti itu lebih memiliki bobot yang lebih dibanding yang sekedar informasi. Oke, nanti kalau sudah selesai kumpulkan dalam bentuk PDF ya. Anda tidak perlu mengirim videonya, tetapi cukup alamat linknya disertakan di file Anda itu ya. Kemudian hasil review ya Anda, yaitu yang nomor 2 itu ditambahkan ya. Kemudian simpan dalam file tugas elemen mesin 2, nama Anda dan NIM Anda. Nanti dikirim, kapan dikumpulkan? Ya, saat bersamaan mengumpulkan jawaban ujian. Jadi ujian akan dilaksanakan ya dengan soal yang berbeda-beda. Nanti saya kirim lewat Google Classroom atau WA ya kepada masing-masing mahasiswa dan dikerjakan. Kemudian jawaban dikirimkan setelah itu ya, setelah Anda menyelesaikan. Ini berdasar selebaran yang dikirim Pak Reddy ke saya ya. Jadi Pak Reddy ada UAS hari Kamis, saya hari Sabtu ya. Masalahnya jamnya ini kok 17.15 sampai 17.55 ini kurang ya. Untuk UAS saya rasa kurang ya, paling tidak 1 jam. Dari Siadu itu jam 16.25 sampai 17.55 jam saya ya, hari Sabtu. Kemudian hari Sabtu itu menurut jadwal yang dikirim dari KPS kok ini ya berbeda. Ya 10.40 sampai 12.40 ya untuk kita berdua. Untuk ujian kelas saya ya, yang dari saya Pak Reddy mungkin hari Kamisnya, saya Sabtu ya. Mungkin kita bisa seperti sekarang, jadwal sekarang yaitu 1 jam saja, jam 11 sampai jam 12, atau sesuai dengan jadwal yang diberikan sistem Siadu itu Sabtu jam 16.30 sampai 17.30 ya. Kalau bisa Sabtu 11.10, 11.00 sampai 12.00 tidak ada komplain dari mahasiswa, saya tunggu komplainnya sampai hari Kamis paling tidak, ya, maka kita akan melaksanakan ujian SA hari Sabtu jam 11 sampai 12.00. Kalau ada komplain karena mungkin berbenturan dengan kuliah yang lain, ya, maka ya saya menggunakan jadwal sesuai Siadu jam 16.30 sampai 17.30. Ya, maaf informasinya mungkin saya tunggu sampai Selasa ya. Saya harus tahu informasinya Selasa, nanti saya koordinasi dengan Pak Reddy. Mungkin saya pakai Sabtu seluruh jamnya dan Kamis biar dipakai Pak Reddy mungkin. Saya Kamis hanya ngirim film ke YouTube saja, Anda bisa buka kapan saja ya. Begitu. Sekian akhir kuliah pada pertemuan ini. Mudah-mudahan bermanfaat ya, tetap sehat, semangat dalam kondisi yang berat ini ya. Kita tidak boleh menyerah. Dan wassalamualaikum warahmatullahi wabarakatuh.